Yeah, I'm going to be assuming that when I show people checkerboards, it causes visual cortex to light up for sure. Cool. So I'm talking about multivariate analysis today. It's a gigantic field. There are dozens of different approaches. I'm going to focus on a couple broad classes of approach, and my goal is to blow through a decade of work, and mostly what I think is the best work, to try to give you a sense of how many different ways there are to do this sort of analysis, multivariate analysis. But I want to start with a really simple example. So imagine that I show people in the scanner a picture of a face or a house. So even maybe 10 seconds you're seeing faces, maybe a bunch of different ones, and 10 seconds you're seeing a house. So I have a bunch of trials where you see a face or a house. It's not Hugh Laurie. When you Google face house, this is what comes up repeatedly. But this is the design, and the question that I have is actually very simple. Given some brain area, I want to know, does this brain area care whether you're seeing a face or a house? So say V1, the first visual cortical area, does it know whether you're seeing a face or a house? The logic is that if it responds differently to faces and houses, something about you seeing faces and houses is happening in V1, or that visual area. So in my hypothetical example, let's say we have 100 voxels, here shown in a 10 by 10 matrix, and that when I show you a face, you see cortical activity on the surface that looks like that smiley face. And when I show you a house, you see voxels light up like a house. This is actually how a lot of visual cortex works, surprisingly, is that you have a map of space laid out on your cortex. And again, my question, this is the truth, but now my goal in analysis is to figure out what is happening in V1 or this area. Does it respond differently? So I simulate some data from this hypothetical example. I can subtract all my face trials from house trials, and you get something like what's on the left in this example. And I can then do a classic univariate analysis. So in the univariate analysis, I model voxels as a function of my condition, just as people have done for a couple decades. And the result of that, the p-values, are shown on the right. And what you see is that of these 100 voxels, there are about 20, 25 that respond significantly differently to faces or houses. And my question is, what are you going to do with this now? You've got a P map here, and it says, yeah, 20% of your voxels in V1 respond differently. But my original question was, does V1 care about faces and houses? And I think it's really hard to make that conclusion from this sort of analysis. 20% of V1 seems to, but we don't know. Is that enough to say the whole area does? Is that a lot of information? A little bit. Here, I'm just doing a bunch of t-tests, no multiple corrections, or especially no cluster analysis. Had I done that, I probably would have washed out most of what I found to be significant. The reason is that my hypothetical example is sparse. The responses of faces and houses, it's not clumped in one part of V1. It's a sparse representation of faces and houses, kind of like the people in this giant room. So the question is really quite different. It's not about a clump of brain activity, it's about a pattern. And so the goal in multivariate analysis is to figure out, does this pattern of brain activity, not individual voxels, but the whole thing at the same time, differ depending on your condition? There are a lot of ways to answer this question. The simplest way, though, is to just flip the linear model that we've been using to do univariate analysis around so that the independent and dependent variables get flipped. So here I've said condition is now a function of voxels times some weights. So it looks very similar to the standard univariate analysis, but instead of trying to predict voxel activity as a function of condition, I'm predicting condition as a function of the voxel activity. And that's it. So the subscripts here show you that on the right now I have a big matrix, my voxel activity, for every trial in my experiment and every voxel. And the beta weights here, the regression coefficients, I now have one for every single voxel in my multiple regression. So what this simple equation does is map the sum of all of this voxel activity onto my condition stimulus. So this is really easy to say or to write down. It doesn't take a genius to say, well, you just flip the dependent and independent variables and now it's a multivariate analysis. It is, but it ain't that easy. It comes with two very serious problems that we have to address. The first problem is that almost always in these sorts of cases, you have more voxels than you have trials in your experiment. In other words, you have more predictors or independent variables than you have pieces of data. It's like if you study cancer and you want to predict cancer outcomes, do you get cancer or not, based on smoking and drinking and socioeconomic status, et cetera, but you only got 3 subjects to figure it out. You have more unknowns than you have data to solve the equation. So this equation is non-identifiable. I can't find one solution. There are a bunch of solutions for these weights over voxels that'll give me a good answer. And what that does, what happens, is that you end up overfitting the data. If you give me 400 voxels to try to account for 100 trials in my experiment, I'll do it perfectly every time. I have too many degrees of freedom. So the goal when you're doing these sorts of multivariate analyses is to somehow constrain this problem to make it manageable. And there are a lot of ways to do it. A lot of them come from machine learning. So you may have heard support vector machine tossed around, or ridge regression, or Bayesian methods with sparse priors. All of these things are tools to try to make that regression equation estimable, to kind of simplify it somehow. Most of them work by essentially making a lot of the weights, the regression coefficients, close to 0. So any voxel that's not really helping you figure out which condition you're in, these methods are going to toss it out the window to try to simplify the problem. I'm not going to talk about the details of these approaches today. You may know there's an entire session on multivariate analysis, like right there, I think. And I assume those nerds are talking about this kind of stuff all day long. But just trust me, for this example, that it's possible, that there are tools that allow us to fit these seemingly impossible problems. But there's a second problem that arises now. Even if you believe me and I say, yes, here's a machine learning tool, it can estimate this equation, the question is, how would I know? How do I know that it's actually working? Because even though I can sparsify the problem, I can simplify it and make the model fit, I still don't have a good metric for figuring out whether it's fitting or not, because I still have way too many voxels compared to data. So the question is, how do you know that the model works? And the answer is an approach called cross-validation that's been standard in machine learning for a long time, and now I would say standard in fMRI. It goes like this. I'm going to take my experiment, my fMRI experiment, and split the data in half. Say the first half of the experiment and the second half. And on the first data set, the training data set, I'm going to fit my model. I'll use something like a machine learning technique to fit the linear model. And what the model is going to do is map activity patterns in voxels onto my conditions. It's going to say, this is what I think it looks like when you're seeing a face, and this is what it looks like in V1 when you're seeing a house. So I've trained my model with the first half of my data. I'm now going to use that model and the activity in the second half of my data to make a prediction. I want to predict on every trial in the second half of my data, was it a face or a house that produced this activity pattern on this trial? So what I'm going to try to do is what's sometimes called decode the stimulus condition that produced those data. So I do that, and then I'm going to flip the training and test sets. Now I'm going to train my model on the second half of my data and use it to try to make predictions about each trial in the first half. So at the end of the day, what I have is a prediction for every trial in my experiment, which stimulus condition led to that activity pattern. So what my dependent measure is now for my experiments no longer mean bold or percent signal change or something like that. It's classification accuracy. I have, say, 100 trials in my experiment. I have a prediction for each one. Was it a face or a house? And I know the truth. It was a face on trial 1. And now I can compute accuracy. How good is the classifier doing? And in my simple face-house example, if there's no information in this pattern, then this classification accuracy will be at chance. Chance here, because there's 2 choices, is 50%. And so if V1 doesn't care about faces and houses, my classification accuracy will be at 50%. But if there is some information in the pattern, classification accuracy will be above 50%. It's dead simple logic. So this approach is sometimes called decoding or neural decoding. It's also been referred to as mind reading. So it's a decade old now, but when it came out, it was in like all these journals, the Science magazine and stuff, like, oh, we can read minds. And it's pretty cool. My favorite reason for mind reading is my parents. 20 years of graduate school, they still didn't know what I did for a living. But you tell them, like, yeah, I read minds with fMRI. They think you're a genius all of a sudden. But the truth is that I think that is a little distracting. It's true. What you're doing in most cases is trying to read someone's brain. You're trying to figure out what are they seeing, for example, based on their brain activity. It's pretty cool, but what I want to try to show today is that it's way more than just a parlor trick. It's actually a powerful tool for doing some serious science. So to finish up with my hypothetical example, here are two examples of a face trial on the left and a house trial on the right. And unless you're some kind of savant, I can't imagine you could look at these patterns and say, oh, that was a face trial, or that was a house trial. It's hypothetical, but it's fMRI. It's so noisy, you have no chance. But the classifier in this case is able to discern with 80% accuracy whether these are face or house trials. So it could probably get this one right. It knows that that's a face on the left. The way it's doing this is by leveraging all 100 voxels at the same time. It's a multivariate or a joint analysis. And the model looks at all 100 pieces of data, which is a ton of information, and can make a pretty accurate prediction. That's a face, that's a house. So this has been going on since the early 2000s, this kind of classification approach. And in vision, which is mainly what I study and what I'll talk about today, it's been shown that you can classify just about whatever you want that someone's looking at. So you can tell what orientation, like which way a line's pointing that I'm staring at, the color of things, where they are. You can definitely do like, are you seeing a face or a house, smiley face, frowny face, and the list goes on. It's exhausting how many studies have been done on this, because visual cortex is very powerful, and these methods are very capable of extracting that information. There's lots of cool examples in other perceptual modalities too. So in auditory cortex, you can decode like the timbre, like what instrument you're hearing, or whether it's a male or female voice. Auditory is really exciting because you can also start to study language and do more complex type of stimuli. Every sense that we have, people have done these sorts of studies. What are you smelling? What are you feeling? Which toe are you feeling? There's way more complex examples too that still use this simple decoding approach, like, are you lying or telling the truth right now in the scanner? Another one, with motor cortex, you can use this classification analysis and say, are you imagining playing tennis or cleaning your house, for example? Turns out these activate different patterns of activity across the motor cortex. This one's terribly freaky, as someone mentioned, because you can have people who have locked-in syndrome. They haven't moved, they haven't blinked for 10 years. And you put them in a scanner and say, hey, if your dad's name is Alexander, think about playing tennis right now. And you do the analysis and it shows tennis motor cortical activity. The family starts crying and the scientists start cheering. But that really did happen. So there's a lot of kind of applications with which you can use these tools. For me, though, my job is to figure out how the brain works. And I'm always amazed at how much mileage we've got out of this really simple question of, can you decode information? Even still. So a couple years ago, we were pretty surprised to find that we could tell what orientation you were looking at if we decoded from the LGN. The lateral geniculate nucleus is the first brain area in the thalamus after your eyeball. And we are able to tell what orientation you're seeing, and then we showed that attention modulated it. This is an area, the LGN, that neurophysiologists have a really hard time getting at. So really simple logic, but it can show us a lot. There's really nice examples that take it a step further. For example, you can play sounds in the scanner, like cows mooing or trucks honking, I don't know. And it turns out you can decode what sounds someone is hearing, but from visual cortex. And the idea is that when you hear a duck quack, you start thinking of a duck. You imagine it, so you can tell in visual cortex. Anyway, lots of fun examples. But that's really just the very tip of the iceberg, this notion of trying to figure out what you're seeing. Very early on, when people start using this approach, Yuki Kamitani and Frank Tong did the same kind of analysis, except in the first half of their, oh, this does work. All right, in the first half of their experiment, they showed just these lines. So for a trial, like a 10-second block, you might see lines pointing this way. And then you might see lines pointing at 45 or 135 degrees. And they trained classifiers to discern whether you were seeing lines pointing this way or this way. For the second part of the experiment, they showed stimuli like this guy, where both of these line stimuli were overlaid at the same time. And you sit in the scanner and stare at this thing, and the instructions are, attend to the white lines. And if you don't study vision, I encourage you to do this for a second. It's pretty crazy. When you attend to something like this, what tends to happen is that the white lines seem really salient, and you can almost make the black ones disappear, like you don't even see them. Well, in fMRI, what they showed is that in early visual cortical areas, lots of them, you can tell what someone's attending to for the same stimulus. So the stimulus doesn't change here. So now what you're decoding from visual cortex is what someone's thinking, what information they're paying attention to. A few years later, Frank Tong took this logic a step further. And in this experiment, this is from 2009, a trial goes like this. First, you see some kind of stimulus, maybe an oriented grading here. Then you see another stimulus that has a different orientation. And then there's a cue. And the cue tells the subject here, remember the second grading. And then after the cue, there's a retention interval. Here it's 11 seconds. I've done up to 30 seconds. It's excruciating for a subject because what you have to do in this retention interval is think about the grading. The instructions vary. You can say imagine it, think about it, remember it because I'm going to test you on it in a second. But you're essentially sitting here staring at a blank screen thinking about some orientation. This has been done with motion, direction, color, all kinds of stimuli, but you're thinking of something. And the trick is that during this period, you can use this classification analysis to figure out what stimulus someone is thinking of. So there's no visual input. It's all in your head. And you can tell from early visual areas what it is that's in there. Now, this finding was really profound because at the time, and still, I would argue, neurophysiologists never saw this happen. For decades, they've been recording from V1, asking monkeys to try to think of a certain stimulus value, and they almost never see activity. But you can tell from fMRI just fine. As an aside, I read this paper in 2010 and immediately emailed Frank Tong to see if he would hire me as a postdoc, and he did, and that's why I'm standing up here today. I spent 5 years doing this kind of work with him. It was really cool and exciting. So in that example and all the examples I've talked about, what you do first is pick a brain region you're interested in. It might be V1, the LGN, PFC, whatever. And then go see if there's information contained in that area. Well, a really, in hindsight, obvious and cool different way to do this is in what's called a searchlight analysis. So instead of picking a brain region and studying it, you say, all right, I'm going to make some kind of chunk of voxels, some shape here, like a 3 by 3 by 3 cube of voxels. And what you do is put that cube somewhere in the brain and then classify from that cube. What is this person thinking? And then you move it over a voxel and do it all over again, and you get classification accuracy. And you move this kind of set of voxels around the brain at each point doing your classification analysis. And what it gives you in the end is a map of where in the brain this information is contained. So in this example, which is just from a couple of years ago, John Sorensis and Ed Esther did this searchlight approach and asked the same question that Frank did. When people are thinking of a stimulus value, they're just imagining an orientation, where in the brain can I read that out and tell what they're thinking? And you can see it's all over the place. I mean, it's certainly not the whole brain, but there's a lot of visual cortex and prefrontal, some areas you'd expect, maybe some not. What I want to highlight, though, is that in this example, and almost every other example of a searchlight analysis, what's happening here is way different than mean bold. So on the right, this is if you do a mean bold analysis and say, where in the brain is there more activity, or sorry, more bold analysis, if you're thinking of something versus just staring at fixation. And you get activity in IPS and PFC in various regions, but it's a really different profile than when you ask the different question of where can I decode what someone's thinking. So these are two different types of information. The mean bold signal mirrors what they find in neurophysiology. There's no mean bold uptick in early visual areas in V1, but we can tell what you're thinking. It's really kind of neat. Okay, so in all those examples, the logic is if it's above chance, there's information there. And sometimes you actually don't want to find information. Sometimes it's really important, like for control analyses, to say, actually, we don't know what you're thinking in this brain area. And an example I'm fond of that we haven't published yet are these shape stimuli. So the one on the left I call convex. You should see it as this kind of shape that pops out at you in 3D from the screen. And the one on the right you should see as concave, popping into the screen. This is an illusion, of course. This isn't a 3D presentation. Your brain invents depth from this texture information. And an entire field of vision science is dedicated to figuring out how it does that and where in the brain this happens. So it's tempting to say, like, okay, well, I'll throw people in the scanner, show them these two stimuli, and say, where can I tell which one they're looking at? But there's a big problem with that. If you look at these stimuli, they don't just differ in their shape, in which way they're pointing. If you take like this little bit here, there's some like characteristics, the way the lines are pointing, how dark it is. And over here, in that same place, everything's totally different. It's different patterns, it's different line orientations. The bottom line is that whenever you're interested in this kind of higher level information, like shape, it always comes with annoying lower level differences. There's always going to be stuff here that's uninteresting. So for example, if I do just do this in the scanner and do a searchlight and say, where in the brain can I tell the difference between that convex and that concave shape, I get the map on the left here. The orange and the yellow are places in the brain where I'm able to discern whether they're seeing convex or concave. And if you know, this is V1 right here at the back, and V2 and V3, it's everywhere. This is the whole visual cortex, basically, because there's a lot of differences between these stimuli. So I can tell which stimulus you're looking at. It's boring, no big deal. So I don't want to talk about what we did, but we did a bunch of experimental stuff to try to get around this problem. We did a lot of stimulus manipulations that we had hoped would make these stimuli so that there's no way a decoder could decode shape based on the more boring low-level features. And what we end up with is the map on the right. So here you see there's activity more where we would expect in what we call mid-level visual areas, but not in V1, V2, V3. The point of this, though, is actually the blue color in the images. So in these images, there's orange and red, and then there's blue, and then there's nothing, no colors on the cortex. What I did here is pass my classification accuracy through a Bayesian hypothesis test. And what Bayesian hypothesis tests allow you to do is reject the null, like in the orange regions, and say, yeah, I can decode shape here, or accept it. So all the blue areas are significantly at chance. There's evidence that you absolutely cannot decode. So a lot of powerful ways to look at even just simple decoding accuracy. But again, everything I've done is chance or not chance, or above chance. And there's another logical step you can take with this same data to do way more interesting things. So for example, it's tempting to think that the better you can classify some stimulus, the more stimulus information there is. And a lot of times this is true. So in this experiment, they showed different gradings of different contrast on the left. And on the right, you can see that classification accuracy increases monotonically with stimulus contrast. So here, better stimulus signal means better decoding. We can also do it here by adding noise to the stimuli. So if I take like a house, and I'll show you faces and houses in the scanner, and I start to add noise to them, external noise, what happens is that classification accuracy on the y-axis goes down monotonically as I add more stimulus noise, as we would expect. This is pretty obvious and a little boring by itself. What's neat is that here, we're actually studying attention. And so I either had you attend to the house or do some other task. And what we found is that attention only did anything if there was a bunch of noise in the stimulus. Here, this is in V1. The point, though, is that by making this assumption that classification accuracy somehow tracks the amount of information in an area, you can make really rich theoretical claims about how then things like attention start to affect that. So for example, the lines in this figure come from a model of signal processing that we're able to fit to the data in a bunch of different visual areas and learn a lot. Simple assumption, but very powerful. Okay, so that's classification. This very kind of simple question, can I tell what information is there? But that's really a small part of the contemporary field of multivariate analysis. The next type of analysis is usually referred to as an encoding approach. It's really a lot like classification with one difference, that instead of using something like a machine learning classifier or like a linear model, you're going to make interesting substantive models of the neural activity and then try to use those to decode. So here's an example from 2006 with Therion and Stan DeHaan, where they took voxels and visual cortex and said, all right, every voxel in the brain we know responds to some particular part of space. So they fit a 2D Gaussian to every voxel to characterize where in space does this voxel respond. It's very simple. So if you have 200 voxels, you have 200 different models now of where those voxels respond in space. That was the first half of the experiment, the training phase. At test, they showed stimuli like this. You might see a cross or an L on the right, these different patterns. What they were able to do is take their models for all the voxels and take a new activity pattern now, like when you're seeing one of these shapes, like this little guy here, this little elbow, and say, okay, given the activity, what is our best guess at what someone is seeing? And so, it's hard to see. The dots, the circles here are what they showed them, and the heat maps are what they were able to draw from the brain activity. So they're reconstructing what you're seeing based on brain activity and trained models. That was a really simple model. It's just where in space does each voxel like. And a few years later, out of Jack Gallen's lab, they took this model and expanded it to a great degree, for example, by saying, all right, every voxel, yes, it has a place in space that it responds, but also every voxel has an orientation preference. Some voxels like vertical lines, some like these lines, and also every voxel has particular spatial frequency preferences. Basically what they did was throw the kitchen sink at V1 and other brain areas and add all kinds of complexity to the model. And I just want to say what they can do with this model, even it's giant and it fits the data perfectly. But by doing cross-validation, they're able to take the model and predict what image you're looking at. They start with 120 images, and they say, can I guess which of these 120 you're seeing right now? And they can with remarkable accuracy. Okay. So this is, again, a parlor trick. I can decode what you're seeing. I can see what you're seeing. But this encoding approach has a really fundamental leg up in doing science. And that is that because the model is substantive, I can build different models, and I can try to figure out what you're thinking or what you're seeing, and I can now test which model does a better job than other models. So for example, when they added spatial frequency and orientation, their model did better. In more recent work, they add in things like language to the model. So before, you're seeing this picture in the scanner of this building, and the model choosing, actually in this case from 6 million pictures, this is what the basic model says from V1. It thinks you're looking at a dog. It's pretty embarrassing. But when they add in language into their model, you get back something that's much more close to what you're actually seeing. So you can test these models by fitting them and then figuring out which model gives you the best prediction. So there are other extensions to this model comparison. And a recent example, again, from us is that instead of just figuring out what you're seeing, one thing you might want to know is how well are you seeing it? So we can ask in visual cortex, for example, if you're seeing the color red, how well does visual cortex encode that? Is it sure it's red, or does it think maybe it's orange? And you can quantify this and use it to make predictions about behavior. I talk about perception because that's what I do. But I'm almost out of time. So I just want to briefly mention that there are a lot of studies that use these approaches that have nothing to do with perception at all. One that I'm very fond of studies category learning. I don't have a lot of time to talk about it, but essentially they have these models of how you do very complex cognitive operations. The models have become defunct. After 50 years of people arguing and making them more complex, a lot of people threw their hands up and said, we can't tell anymore how people categorize because the behavioral data just can't tell us. Well, recently, Mike Mack figured out a way to use multivariate pattern analysis and brain data to say, hey, we can actually test these models by applying them to brain activity. We can look in the brain, even though the behavior won't tell us which model is right, and we can test these models to say, what model gives us a better picture of what the brain is doing? So, very rich. All right, I'm out of time, so I actually want to mention two things. One is that I've barely scratched the surface. There's such a rich field here of different analytic approaches, and they're applicable in just about any substantive question you can think of. I've skipped most of them. I've also skipped a lot of the analyses. The one I want to mention in particular is called representational similarity analysis. I don't know if he's here, but Nick was talking about this. He invented it, so I'll let him talk about it tomorrow, I imagine. And much of the stuff I talked about today, we've actually written a couple review papers, and everything I talked about and proper citations are in those, and there are a lot of great review papers on it. Thank you very much. Yeah, I thought I was done. I have 2 minutes. It's an angry red light blinking.
Okay. Thank you for your talk. I have a question about your slide where you talked about significantly at chance decoding.
Yes.
So I'm under the impression that you could get chance performance for a lot of reasons. For example, you're using a linear classifier, but the information cannot be read out linearly. So how can you make an assertion that the information is not contained in a particular brain region?
That's a great question. Yeah, not a linear model, or they moved, or it's fMRI, so it's just a bunch of noise. No, that's a great question. The logic usually isn't just showing that something is at chance. What you have to do is first show, here it's above chance. Then I did something interesting, and boom, now it's at chance. So in that situation, what you're looking at is essentially an interaction. So in that case, you can really say that whatever it did, like your stimulus manipulation, it removed the information. But you still have to be very careful, certainly. So thank you.
All right, thank you.